Good morning, everyone. It's a pleasure to be here in person and talk to you about reactor neutrinos, what we have learned at short baseline, what the open questions are, and how we might be able to search for physics beyond the standard model. Before I get started, I wanted to thank the organizers for inviting me. It's great to be back at KITP and see you all in person. So in this talk, I will give you an overview of the recent developments with reactor neutrinos. And just to orient you, neutrino experiments at reactors use neutrinos with energies of about several MeV. So we are studying antineutrinos that are emitted from the beta decay from the fission reactions in a reactor. And so we are talking about MeV type neutrinos here. With these neutrinos, we have been able to do a number of discoveries over the past few decades. It started out, of course, with the first observation of the neutrino at a reactor in 1956. And in 1995, Fred Reines from UC Irvine received the Nobel Prize for it. In 2003, we did the first observation of reactor antineutrino disappearance with the Camland experiment. And then in 2012, we measured the mixing angle theta 1,3 with reactor neutrinos at the Diabé experiment. So over the years, reactor neutrinos have played a really important role in helping us understand neutrino oscillations and the property of neutrinos. And of course, now there's still a very active suite of experiments that I will describe that are probing neutrino oscillations and are searching for deviations from the three-flavor paradigm. To orient you in the landscape of oscillation physics, this is a plot that shows a variety of experiments, their distance, and the energy of the neutrinos that they use in the neutrino oscillation landscape. And what you see here is that it covers several orders of magnitude in distance and in energy. And the experiments that I will focus on are in this lower corner here. It includes the short baseline reactor experiments like Prospect, Neutrino 4, NEOS, the little longer experiments like Diabé, and I will also touch on the gallium source experiments as they're relevant for understanding the landscape in this sector. I will not talk about all the other neutrino oscillation experiments, accelerator-based experiments that also contribute to our understanding of neutrino oscillation physics. I wanted to point out how big of an effort the reactor neutrino experiments are worldwide. This is a map from a recent SNOMAS white paper that shows the suite of experiments that have operated worldwide or are still ongoing, and some of them are actively planning upgrades. What you see is that there's a large distribution of experiments. A lot of them use the inverse beta decay reaction to detect antineutrinos from reactors. Some of them are based on coherent nuclear scattering. And it's also important to point out that a variety of reactors are being used to study reactor neutrinos. They are the low enriched uranium reactors. These are typically power reactors that we find as electricity generating reactors. And then there are the HEU reactors, highly enriched uranium reactors, and their advantage is that the neutrinos come essentially just from one single isotope. These are typically research reactors, and they are much fewer and have less power. Reactor neutrinos are a unique tool for studying neutrinos and neutrino oscillations. And the reason they are unique is that reactors give us a pure nu E source, nu E bar source. So electron antineutrinos come out of the beta decays in the fission reactions. And from knowing the isotopic composition, we can make a prediction of the total flux and the energy spectrum of reactor neutrinos coming out of a reactor. And what you see here is the predicted fission per MeV per isotope as a function of energy. So you see we're looking at an energy range up to about 10 MeV. And when you fold this in with the cross section, then this is a typical spectrum that you might see in a reactor neutrino experiment. The mean energy is about 3.6 MeV, and that means we can only look for the disappearance of electron antineutrinos. We are not looking for appearance experiments here. Now, it's also important to point out that the vast majority of all antineutrinos come from only 4 isotopes: uranium-235, uranium-238, 239 plutonium, and plutonium-241. So with these 4 isotopes, we can predict essentially the entire antineutrino flux coming out of a reactor. Before I get to the current experiments, I just wanted to give you a brief history to give you a sense of how far we have come in the past few decades. The field has really been around for a while, and in the early 80s, there were experiments to measure the spectrum of reactor neutrinos at various experiments. And one of the experiments at ILL in Grenoble defined the field. And this is a measurement from 1981. So you see the reactor antineutrino spectrum with about 5,000 events, and there was about a 20% uncertainty on that. Since then, people have done a lot of work to understand the spectrum coming out of reactors, understand the flux predictions, and the uncertainties were reduced. And in the end, in the 1990s and 2000s, we thought that we might understand the reactor antineutrino flux to a few percent, and this was confirmed with experiments. Now, as a reference, here is a blow-up of the 1981 ILL experiment. So again, you see on the right-hand side here, the prompt energy spectrum of the positrons which you detect in your experiment. And so this is the type of energy spectrum that we'll be looking for. Again, for reference, this was about 5,000 events. Since then, we've come a long way. It was in early 2000s that a much bigger reactor experiment in Japan, the Kavli experiment, detected the neutrinos from 55 reactors that were operating at the time in Japan. This was, of course, before everything was shut down there. Kavli was situated in the Kamioka mine, and it measured the total integrated flux from all of these reactors with a flux-weighted distance of about 180 kilometers. And what Kavli, of course, measured was a suppression of the flux. So that was the evidence for reactor neutrino disappearance. It saw that the energy spectrum that we observed was not what was expected, but in fact, it had this spectral distortion, which was a clear indication of neutrino oscillations. And if you put this in a plot that shows the distance over energy, you get the very clear signature of oscillations. Following the discovery from Kavli, we looked at different distances, and one of the experiments that did this was the Diabei experiment in China, where we built an array of 8 detectors at 3 different distances from 6 reactors that formed the complex of the Diabei reactor power plant. We again use liquid scintillator detectors using the inverse beta decay reaction. In this case, we had actually built the liquid scintillator to enhance the background suppression and the detection efficiency. And this experiment started operating in 2011 and operated until 2020. Now, what Diabei, of course, saw was also that over a distance of about 1 kilometer, you saw oscillations. And this allowed us to map out the oscillation probability in this effective L over E range. And from that, you could extract the neutrino mixing angle, theta 1,3. And here are some of the results from the later Diabé publications. And you see a very precise measurement of the reactor antineutrino spectrum with many, many more events. We have now millions of events, and that allows you to determine theta 1,3, or in fact sine squared 2 theta 1,3, and the appropriate delta m squared, very precisely. And we've now reached precisions of about a couple of percent in those parameters. Now, what the results from Diabé and some of the other experiments worldwide indicated was, though, that there's more going on that we didn't quite understand. And there were two effects that led to the so-called reactive neutrino anomalies. One of them was that the total measured number of neutrinos was less than what was predicted. If you look at the measured reactor flux as a function of a distance versus the predictions, you see that it's typically less than 1. This is a plot that shows previous reactor experiments at different baselines between 10 and 100 meters and up to 1 kilometer. And the red data point here is Diabé. And it showed that there was a deficit of about 5 to 6%. In addition to that, we also saw in Diabé and some of the other experiments like Double Show and Reno in Korea that there was a spectral deviation in the region of about 4 to 6 MeV. There was an unexplained bump in the spectrum. And all of the experiments, all of the theta 1,3 experiments saw this. So this prompted the field, this prompted us to think about, is there more going on? Understanding the reactor flux and spectrum really required more and additional data. The deficit was one effect that sparked a lot of interest in the community. And the reason this was because people speculated that maybe this deficit was due to the existence of a fourth neutrino, the so-called sterile neutrino. And this is a plot that again shows the reactor flux measurements as a function of distance. This is now up to 1 kilometer here. And this is the red line indicates what you might expect from a 3 neutrino oscillation scenario. If you had a fourth neutrino, a fourth sterile neutrino with about an EV squared mass splitting, you would get the blue curve here. So that could explain this deficit. Now, and this came about because there was a reanalysis of the predicted reactor flux in 2011 that shifted this and caused attention with the global data. On the right-hand side here, I show in an oscillation parameter space all of the Newey-Bar disappearance data that existed at the time, including gallium data, which I will get back to later, but also showed a deficit. And so we will get back to the gallium data, which showed a deficit, and the short baseline reactor data. And again, there was hope or speculation that maybe an EV scale sterile neutrino could explain all of this. Now, before I go into the current experiments, let me just say that the search for sterile neutrinos and beyond the standard model physics, of course, is something that is of interest to everyone in the field. This plot here shows constraints, existing constraints on the mass of the sterile neutrino and its squared mixing. And so you see again, it covers a broad parameter space. And the short baseline reactor experiments can cover a corner of this. But there's no a priori reason why we shouldn't be looking for something like this in this corner. There's no strong preference for the mass scale or coupling strengths based on the models. So it's really a search over a broad parameter space. As I mentioned before, the spectral deviation that we saw in the theta 1-3 experiments, this bump, was seen in all 3 experiments worldwide, Diabe in China, Double Show and Reno. They all saw this bump, but no one could explain it. And it was speculated that maybe this was due to our understanding of the nuclear models. There was no other physical process that we could imagine that could create such a bump. Before I go into the new experiments, let me just say that predicting the antineutrino flux in the spectrum is quite complicated. I said at the beginning that in principle we can do it, but basically there are 2 approaches to it. One of them is that you sum up the spectra from thousands of beta branches from in the reactor using nuclear databases and come up with an ab initio prediction of what you might be seeing. This is complicated. There are uncertainties in the database and the databases are incomplete. The second version is that you do take an empirical measurement. There was one done in the 1980s, and you do a beta conversion and you fit things with virtual branches and you get a predicted spectrum. But again, there are some uncertainties in this. So the takeaway here is predicting reactor spectra is complicated and there are significant nuclear physics uncertainties. With the high precision data that we have from Diabe and other experiments, we have been able to look at the contribution of the different isotopes. And this has to do with the fact that the power reactor experiments measure the flux from the sum of the isotopes, the sum of the 4 isotopes. When you burn up fuel in a reactor, you get a conversion. And so the effective amount of uranium and plutonium changes in the reactor. And you see this in this plot here. This is a fission fraction as a function of plutonium during a fuel cycle, and you see how it changes. So with the high precision data from Diabe as a function of time, we have been able to separate out the uranium and plutonium contribution. And we've been able to compare it to models. And the discrepancy that we have found suggests that there was an incorrect prediction for the uranium-235 spectrum. So by measuring the reactor spectrum very precisely with Diabe, we have uncovered that it's likely that there's a nuclear physics solution to some of the anomalies that we have seen. This is perhaps more detail than we need for this talk, but I just wanted to show you the kind of results that you get from the high precision reactor experiments. On the right-hand side here, you see essentially the fission fractions for 239 and 235. So you can make these correlation plots and you get these contours from the Diabe experiments, the other experiments, predictions such as Saclay and Huber, and from the reactor rates. And you see there is some tension, and experiments have been trying to sort this out. So based on this, these results, it was concluded that we cannot rule out the existence of sterile neutrinos, but it is likely that nuclear physics plays an important role there. And this is a plot that was included in the recent SNOMAS contribution. This is now the state of the art. Again, it's a plot that shows the fraction of 239 versus 235 and the different contributions of the experiments, the constraints from other short baseline experiments like stereo, the rate evolution from experiments like Diabe, and you put this all together and you get these constraints. Now, to sort through all of this, the idea was to do an experiment at a reactor where you have neutrinos from only one isotope. And that leads you to do an experiment at a research reactor with a highly enriched uranium core. And so we conceived the prospect experiment, a precision oscillation and spectrum experiment, The idea was to do an experiment that is dedicated to searching for short baseline oscillations as a possible signature of sterile neutrinos, and also do a precision measurement of the U-235 reactor spectrum. And this was an experiment that utilized a new kind of detector, a segmented detector, lithium loading to get very good efficiency in your signal identification and very good background discrimination. Here's just a picture of the experiment when we built it back in 2017, before it was installed and operated at Oak Ridge National Lab. Prospect was one of a few short baseline reactor experiments that operated in the last few years. There was Stereo in France, similar technology, but gadolinium loaded. Solid, a UK-led experiment that operated in Belgium. Neutrino 4 in Russia, and Prospect in the US. All of these experiments were roughly the same size, a few tons, and they looked at neutrinos over distances of a few meters up to 10 meters. From Prospect, we have some of the leading results. So we measured the U-235 energy spectrum very precisely. We looked for the bump that was observed in the theta-13 experiments. We saw something that is consistent with the theta-13 experiment, but not quite the same size. The feature that we identified was about 80% of what Diabase saw. And we also didn't see any sterile neutrinos. So we could place limits on the oscillation parameters in delta n squared and sine squared theta-14. And what you see on this plot here is the best fit from the original reactor antineutrino anomaly, which was the discrepancy between the measured flux and the predicted flux, and the limits from Prospect. And we excluded that at 98.5 confidence level. Other experiments like Stereo did similar measurements. This is the Stereo experiment in Europe at Grenoble. They also measured the spectrum. They also found no signs for oscillations, and they placed limits on the possible oscillation into sterile neutrinos. And in addition to that, they also made a measurement of the absolute flux, which they found to be consistent with the world average. So you see that they were consistent with the previous experiments. Now, there was another experiment in Russia, DANCE, which used different technology. It was a highly segmented plastic scintillator-based experiment, and they put this on a stage that they could move. And this experiment is actually operated inside a power reactor near an extended core in a power reactor. They can move the stage up and down, change the baseline to the reactor core, and in this way probe for neutrino oscillations. Again, they didn't see any evidence for sterile neutrinos, and they placed the limit in the appropriate parameter space. So there's quite a suite of experiments, and I just wanted to show that two of them, DANCE and NEOS, when they looked at the ratio of the expected spectrum to the predicted spectrum, they saw data like this as a function of prompt energy. So something that is consistent with zero, but if you look hard, maybe you see a wiggle in there. But it's important to point out that none of them claimed a signal. So they set oscillation limits, but none of them claimed a signal. There's one big exception in the field, and that is the Neutrino 4 experiment. It's another short baseline reactor experiment based in Russia. They have a detector segmented, liquid scintillator based with PMTs. that's on rails that they can move back and forth from a reactor core. And so they have reported an oscillation signal. This is their data. So you see here, again, the ratio of what they've measured over prediction. And this is as a function of L over E. So they see this oscillation and they claim that they have actually discovered a signal. Now, I have to say that there's quite a discussion in the community about this. We also wrote some papers. There's a poor agreement between the measured and the predicted spectrum. They have not, to our assessment, taken into account all nonlinear effects, the way they model the detector response, the way they calibrate, all of this. So there are some serious questions about this analysis. Nonetheless, they claim to have seen a signal. And if you place this in the oscillation parameter space, they sit somewhere here. This is a very busy plot. This is roughly at a few EV squared, 7 EV squared. What you see here also is the region of the original reactor anomaly. So they're a little bit outside of that. And here are other constraints from Katrin and so on. Now, the other interesting puzzle in the field that was renewed recently came from the radiochemical experiments. And there's an experiment called BESS, the Baxan experiment for sterile neutrinos. They use a chromium source inside an experiment to irradiate a target of gallium. So this is the scheme of the experiment. They have 2 regions of gallium, an inner region and an outer region. They irradiate them with the source. They look at the number of events. And what they see then is that they see a deficit. And the deficits that they measured are actually consistent with the previous experiments that were done with gallium during the time when people looked for solar neutrinos. And there were the GALEX and SAGE source experiments, and they measured in a single container a well-known deficit. This remained a puzzle in the field for many years, and what they found was that the predicted rate based on cross-section calculations, etc., was about 0.95, and they saw about 80% of it. And the recent BEST experiment essentially confirmed this. And if you put all of the data on one plot, this is what you get. So the BEST experiment is consistent with the earlier source experiments from SAGE and GALEX. Now, where does this leave us? If you put all of this together, the BEST experiment, gallium, and the other short baseline experiment, you get a plot that looks like this. This is delta m squared versus sine squared theta 1,4. You have here the allowed region, best fit region from the gallium experiments. You have the reactor anomaly region sitting over here. In gray, you have the variety of constraints from the short baseline reactor experiments. And in red here, you have the claimed signal from neutrino 4. So it's a pretty messy situation. BEST and the gallium experiments are largely excluded by the short baseline reactor experiments, but not completely. And in the middle of that, we have the unconfirmed signal from neutrino 4. Now, here are a couple more plots that tease it apart a little bit. On the left-hand side, you see the constraints from the reactor rates, the reactor anomaly. You have neutrino 4 sitting in there, and the exclusion from the short baseline reactor experiments. On the right-hand side, we've overlaid the microboon allowed region and the microboon exclusion limits, as well as the exclusion limits from the reactor experiments. Now, where do we go from here? In my last couple of minutes, let me just give you a brief outlook to the future. So there are proposals to continue to search for short baseline oscillations with reactors. One of the proposals is the Prospect 2 experiment, where we plan to upgrade the Prospect experiment, improve it, and run for about 2 years. And with that, we would be able to cut into much of the parameter space. This is Prospect 2 with 1 and 2 years of data taking, and you can see that we would cover much of the parameter space that's currently in question by the various experiments. Now, if you think about where we are right now and where we might be in the future, this is a comparison that shows this. On the left-hand side, we have the current constraints. This is labeled now, and the unresolved parameter regions. And this is where we might be in the future if we run Prospect 2 and get additional data from the DANCE experiment in Russia, as well as Juno, Tau, new experiment in China. Now, we also like to dream big, and we have been thinking about how we could build the ultimate reactor short baseline experiment at a facility like the high flux isotope reactor at Oak Ridge in the US. If we have an experiment with about 20,000 liters active volume, which is 5 times Prospect, a little bit longer, signal to background of 10 to 1, we can get about 1 million events per year. And with this, you can really then probe this parameter space very definitively. So this is these contours here for 1, 2, and 5 years. And if you put this all together, 5 years of such an experiment with the expected limits from Katrine and the existing reactor limits, then you have essentially covered all of the parameter space of interest. Before I conclude, let me just throw in one more cross-check that we've been thinking about. And this is using the data that we might get from the Project 8 experiment. Project 8 is an experiment designed to measure the neutrino mass. It's going to be looking for deviations near the endpoint or deviations in the single beta decay spectrum. Now, if there's a sterile neutrino, it will change the shape of the spectrum near the endpoint. And so we've recently looked at how this would allow us to constrain this parameter space. And this is a plot from a recent snow mass contribution that shows in delta m squared versus sine squared 2 theta 1 4, 3 phases of Project 8 with molecular tritium, atomic tritium, and the final phase 4 of Project 8. And so you see that you're starting to probe also significantly the parameter space of the reactors and the best experiment, as well as the best fit values. So with that, I will come to my conclusions. And reactor experiments over the years have made high precision measurements of the prompt energy spectrum from both power reactors and highly enriched research reactors. It now seems likely that an incorrect prediction of the U-235 flux is a primary source of the anti-neutrino rate anomaly. We have not seen any significant indications for sterile neutrinos in multiple experiments, Prospect, Stereo, DANCE, NEOS, except there's one experiment, Neutrino 4, which claims a signal, but it's still actively debated. The best experiment confirmed the gallium anomaly with high significance, but it's in strong tension with the other short baseline experiments. There are a number of short baseline experiments still ongoing, being proposed as upgrades, as well as Katrine and Project 8 that will weigh in on this parameter space in the coming year. I'm not going to say much about microboon. We have the experts in the audience here, but microboon has not confirmed LSNB and miniboon, though energy exists, but has also not completely excluded it. And so with upgraded plans like Prospect 2, we're in a position to significantly expand the short baseline program to search for any signs of beyond the standard model physics. Thank you.
Thanks so much, Karsten. Do we have questions? Yeah.
So I have one quick question and one quick comment. So the question is in the project 8 plot, why does the line become dashed at some point? The red line, yeah. No, the red, blue, and green lines, they become dashed after 10 to the minus 1.
Yeah.
Does that mean something?
Yeah, it has to do with runtime and where exactly we run the experiment with the parameters. Yeah.
Okay, and then I have a comment, which is I was going to make the comment, but it's shown in your slide 35. This best anomaly is completely ruled out by solar data in a very robust way. And I hadn't thought about this before, but it's very clear in this yellow line there. And this is a ridiculously robust bound, unless you do some very sophisticated physics, as far as I understand.
Yeah.
So again, there's something exciting going on there, but it's probably not sterile neutrinos because the solar data would have seen that very, very cleanly, I suspect, because this is a huge effect.
Yeah, that's correct. I did not mention the solar neutrino band, and there have been recent proposals for how to resolve this. When there's been a recent paper on that perhaps some charge current non-standard interactions could explain best that would not show up in the sterile experiments. That is correct, yes.
Yeah, thanks, Karsten. It was very nice. I have one comment on the short baseline accelerator program. So first of all, you had a plot in which there was some microboon excluded limit. I don't know where this is coming from. That's my first question, because microboon has not released any exclusion plot. So I don't know where it's coming from. And then I think I have a general comment. In your last slide, you only mentioned microboon. Yeah. Actually, there is the entire short baseline program, which is exactly one of the goals is to investigate completely the question with accelerator, which is entirely different from microboon, whose goal was to test only microboon, miniboon, and only that. So, okay, just to be sure that the message is a little bit more elaborated. The other question instead related to all this measurement, there are, as you said at the end, the most probable explanation is probably something in the calculation. So what is planned to do there? Is there any plan to improve the calculation, or just or do new measurement or more sophisticated measurement is the answer to all of that?
So first of all, thank you for pointing out, of course, the SBND program. In this talk, I focus only on reactors and short baseline. I didn't have it.
Since you mentioned.
Yeah, absolutely. And this will be a significant part in probing and testing short baselines. As far as the other efforts are concerned, there is a lot of work going into understanding the nuclear data right now. There have been dedicated workshops and efforts to understand this. So this is constantly improving. And what I showed here is a reflection. I didn't have time to go into all of the details, but there are recalculations, there are recompilation of data. So all of this is now going into understanding the prediction of the reactor fluxes. There are ideas to measure them, but going back to actually what was done in the 80s is very difficult and very time consuming. And so far there is no specific experimental proposal to redo the ILL measurements,
the
for
basic.
example.
Yeah.
I'm going to comment on this, Michael.
Oh, excellent. Great.
I have a question about Project 8 and Katrine. You showed separately exclusion contours from Katrine and expected ones from Project 8. Do you have a plot that shows them both?
Let's see.
I can probably do this with PDF after
yeah.
looking at your slide.
So I try to stick to all of the public plots that have also recently appeared its no mass contributions. So this is the current Karsten exclusion. There are probably more projections also from Karsten in their recent papers and white papers. In terms of combined, I have to look at that. I don't have it in here, but yeah.
I mean, basically, my question is for the project 8 projected sensitivities. What does it mean in terms of effective neutrino mass? What is the equivalent assumption in effective neutrino mass?
Yeah, so this is something I didn't include in here, but we're currently mapping out the program for phase 3 and going out to phase 4. Obviously, in phase 4, we want to get down to 40 millielectron volts. Phase 3 might reach fraction of an EV or several EV, depending on where we are in terms of runtime. These are some of the projections that we're working on. There is a plot. Let me just see if I can, actually might have it as a, yeah, let me just show you that. Since you asked about this, I didn't want to get into the neutrino mass business for this talk, but this is our current project 8 projection. So what you see here is the projected sensitivity to the single beta decay mass EV squared. This is where phase 2 is, where we're currently with various demonstrators and prototype experiments. We hope to get down to essentially a limit of 40 milli EV eventually.
Okay.
So that maps out in one graph the project 8 program over the next years. Yeah. I should also point out, of course, that Karsten is a running experiment, and they continue to take data.
So they may improve their contour eventually.
Yes, but I'm not part of Karsten, and I don't have those limits right now.
So another unrelated question is for the gallium anomaly. How well known is the neutrino flux from the chromium source?
That is well known based on also the thermal measurements of the source. If I recall correctly, it is at the % level, so it is precisely. I don't have the exact number.
Much smaller than by 10 sigma or so.
So I mean, it is a robust signature, and I think especially the best experiment renewed the interest in really understanding this. But we have to resolve the tension with the solar constraint and the other experiments.
Yeah, I'm still curious about the neutrino 4 data, because it seems that they have a peculiar setup compared to other reactor experiments. So what are the prospects of taking more data? What are the plans of understanding this data? How is the community working on that?
Well, so neutrino 4 has taken data. They're planning to take more data. They are continuing to publish papers. We have written some responses to their analysis, asking questions. There have been more recent papers that have addressed some of the concerns, but I think it's fair to say that there are still significant questions about how they handle systematics, their energy response, all of these things. At this point, I think it's probably fair to say that a large fraction of the community is not yet convinced, given these questions about how they handle the data, that this oscillation signal is real. We have no direct way of checking it except doing other experiments. Now, the existing experiments have already essentially constrained this. So if you look at where we are, this is neutrino 4, roughly 2.5 sigma effect. These are the constraints and limits from multiple other experiments. So from that point of view, it's already ruled out. It's significant.
I know, but it would be nice to understand what is going on, right?
Absolutely.
So, and they are planning to take more data.
They're planning to take more data. Whether it will change what they will report, I don't know.
Okay, thanks.
All right, we have time for one last question.
Hi, yeah, so kind of moving forwards, I guess the current landscape with maybe 5 experiments or so running at the very short baseline was the correct way to go in the last few years with all of the odd things that seem to appear in this landscape. But you showed a couple of slides about what you could do with some hypothetical larger experiment. Do you think that the community is going to come together and try and build one big experiment to rule out everything, or how do you see that evolving?
So I think in terms of upgrading one of the experiments, I think it's a real option. So we have essentially the site at Haifa at Oak Ridge. So if we can get funding to upgrade the prospect detector, and at that point we would certainly be open to enlarging the collaboration. And there's no plan to continue this kind of program at ILL in Grenoble. Stereo has concluded. Solid has no results yet. I believe DANCE and Neutrino 4 in Russia plan to continue. In the current situation, I don't see them coming together with us to form one collaboration. But I think there's a good chance that if Prospect gets upgraded and that it could run at Oak Ridge, and it would unify part of the community, absolutely.
Okay, thanks. Yeah, it seems like one bigger experiment now might be the way to go.
Absolutely.
Yeah. Okay, thanks.
All right, if there are no other questions, let's thank Karsten again.